Log on, tune in, find out. Another good idea from Cambridge.
Okay, so this talk has nothing to do with any of the talks you've heard so far. So if you'd like to go punting with the rest of the Bayesians, you feel free. Oh, that was when I was one of the few people that prepared my talk before coming to Cambridge. Everyone else has been up there preparing their talks. So I want to thank Steffi for inviting me to this conference, and also Barbara and Rosemary for inviting me to the whole thing, which I really appreciate. And I want to say a word about my friend Val Fedorov. Someone was telling me, isn't it nice how we've got all these industry people together with the optimal design people? And I just wanted to say that Val Fedorov's been doing that for us for 10 years or more with his affiliation with GSK. And also, I've been to so many meetings where there's this little GSK logo. And that GSK logo means that he was actually successful in getting funding from GSK. And I just want to say that I appreciate the contribution you've made to these conferences over the years.
But no more.
Yeah, well, that's why I'm saying it now. So.
It's not true. Val managed to take a forward position on the funding for MODA, I think. Is that right?
Well, they got it in just before they fired everyone, right? Yeah, okay. All right, I guess I can go back and, so I'm going to talk about principles of response-adaptive randomization, which has nothing to do with the doses you've been talking about for 2 weeks now. And there's my outline, and we'll just get right to it. So I want to just bring up the basic setup, the notation. So I have, I really like using this, 2 treatments, A and B, and I have a randomization procedure. So this talk's on randomization, which you haven't heard much about, unless you went to the cluster randomization talks, which were really quite fascinating. So we have a random vector T, which is a randomization sequence, which is just binary 1 or 0 if you're assigned to A or B. And the patient responses I'll denote by X. So at the end of the trial, we have the numbers allocated to each treatment, which are then random variables in my setup, and that's NA and NB. And I'm not going to do the sequential analysis approach where we would have a random stopping rule. I'll just have a fixed N for this. And then a randomization procedure is completely defined by its allocation rule, which is phi j, which is the probability that you assign the next patient to A, given all your past history. And if the past history just depends on the treatment assignments, then the randomization procedure is called restricted, and that's often used to try to balance treatment assignments. And if it depends on the treatments and the responses, then I call the randomization procedure response adaptive. So this history, or sigma algebra Fj, could also involve covariates, and a number of people are interested in this subject, including me, but I'm not going to talk about that in this talk. Now, when I talk about, I write papers on the theory of randomization, and one of the assumptions we make in the theory of randomization is that we want every patient to be randomized with a probability between 0 and 1, not including 0 and 1. So nothing's deterministic here. Now this is different from the way clinical trialists might approach the subject. They like sometimes to use blocks in which many of the patients are assigned with probability 1. Of course, most clinical trialists don't really care much about randomization at all. And as Rosemary would say, they're more concerned that they think randomization is allocation, which someone who works in the theory of randomization wouldn't think that. And then they often say that, well, we do some kind of randomization scheme. It doesn't really matter what kind of randomization scheme we do. And then we do blinding, which prevents selection bias. So I'm going to talk as a randomization theorist rather than as a clinical trialist in this talk. Okay, so a lot of this stuff is in this book, and I bring up this book because I almost made a sale. Okay, so this has been, it's been zero for so long that, it hit its toxicity, and then it just, when the last library bought it. But France came up to me and she said, "I just bought your book, Michael." She thought I was Michael Rosenberger, who has a recent book on adaptive design. So I went from, and it's with no ER at the end. So I went from 0 to 1 to 0 again very quickly. Okay. But most of the stuff is in this book. So I'm going to give some principles on response adaptive randomization, and I'm going to start the way all good statisticians should start in designing, by thinking about what our objectives are for the experiment. So we may have many objectives for a randomized experiment. One might be maximizing power, another might be minimizing expected treatment failures. Minimizing cost, achieving perfect balance may be an objective, although I'd like to point out that achieving perfect balance and maximizing power are often confused, but balance does not always imply more power, particularly when you're in the nonlinear case, or the heteroscedastic case, I should say. So we assume that the underlying responses arise from an exponential family with some parameter vector theta, and based on some optimality criterion, I'm going to want to target some optimal allocation. So this is a design problem, but we only have 2 treatments, so it's a mini design problem, and all I'm going to do is select the weights in Val's notation, right? I want the weights of this design. So that's going to be my allocation function, rho, which is in the response adaptive randomization setting is going to depend on theta. So my goal is to find, quote, a good randomization procedure that converges to this target allocation. So NA over N is the observed proportion, so I want that to converge almost surely to this allocation function. So I'm going to assume that first, as an example, that we have binary response. So we have x arising from a Bernoulli distribution and the parameter vectors PA and PB, which are the success probabilities. So what are the kinds of allocations that may be optimal for some of our objectives? Well, if you want balance, obviously the objective is a half. Now you can do a little optimization problem which actually derives from, Chris and I were talking about where this actually derives from. He credits it with Turnbull, I think. So let's say Turnbull came up with the idea that you could minimize a function like NA A of theta plus NB B of theta. And what I can also do is I can fix the variance under the alternative to a value, solve for n, plug it into this, and then minimize the other criterion. And I was told by someone in operations research who's an optimizer that that's called Pareto optimization, although I'd never heard of it, where you fix one criterion and minimize the other. And then you get a dual problem that the fixing one and minimizing the other is equivalent to fixing the other and minimizing the, so many of you know that already. So these things come from this dual formulation of the Pareto optimization. This one is just maximizing power, which you'll recognize as the ratio of the standard deviations. But we could also fixed power minimize the expected number of the expected treatment failures, and you get a slightly different allocation, root PA or root PA plus root PB. Interestingly enough, this David Azrael submitted yet another paper, the one that Nancy was talking about. I mean, his thesis just must be the most incredible piece of work of all time, because he's gotten 4 papers out of it now. But he submitted another paper showing that one of his points was that this is often not terribly different from 1/2 unless you get really spread out between PA and PB. This one does make a difference, but it's it doesn't go too far away, because you still want to, it still fixes the power. So now there's a number of, for about, I guess my first 8 years or so, I worked on properties of EARN models, and there have been a number of EARN models that have been proposed, and perhaps we kind of did things backwards when we looked at EARN models. We kind of defined a design and then looked at what happened to it, rather than defining a criterion and design to get to that criterion. So this is the backwards way of looking at the problem. And it turns out all of these EARN models converge to QB over QA plus QB, which is a property of the procedure. And I've never found an optimality criterion that gives us this allocation as anything optimal. So, this is all the EARN models that I know converge to that, including what's called the randomized play the winner rule and the drop the loser rule. Now, there's another class of problems that don't use this formulation, but that's targeting a different objective. And that's the class of problems that I think Robbins first talked about, and then Nancy's worked on some of these problems. And those are designs that converge to 1 or 0. So all the patients eventually get the best treatment. These are a different class of problems. Here I'm actually interested in what clinical trialists are generally interested in, and that's comparison of a treatment effect at the end. I want to be able to compare a treatment effect. So this is not a design that converges to that eventually all patients will get the better treatment. So that's a different class of problems. Nancy has a paper in the Annals where they use Martingale's techniques to show that you can actually do some inference about the treatment effect following these 1 or 0 convergence designs. But that would not be the design you would select if your goal was to actually estimate the treatment effect or to do inference on the treatment effect. So we move over now to another example, and this is if we had normal responses where we have mu A sigma A and mu B sigma B. And if we wanted to maximize power, which this is the d-optimal design for this problem, is the Niemann allocation, which everyone knows is just the ratio of the standard deviations. And if you wanted to minimize the maximum eigenvector of the inverse, they use the e-optimality criteria. You get the ratio of the sigma A squared over sigma A squared plus sigma B squared. And Giovannioli derived that. And here's another design that's equivalent to the design on the previous slide. For fixed power, minimize the expected mean response if mean response is bad, if a high response is bad. And in this case, you get a messy function of both the variances and the means. And in fact, this allocation here can put more patients on the inferior treatment. And so you can stick a half in there in that event. So this is just examples of how you can get different kinds of allocations for different problems. So now what's the next step? So we have this allocation. We'd like a design that targets this allocation in some sense or converges to this allocation in some sense. So with the exception of the non-adaptive response adaptive case where you're targeting 1/2, the target allocation, because of the nonlinearity of the problems, and it's going to depend on the unknown parameters. And so we want to do some kind of sequential estimation of these unknown parameters. And so we're going to have an allocation function. This should be NA over J. So we want an allocation function that's dependent on both the observed allocation proportions and the estimated target after J patients. So one obvious function is just to assign patients with the probability that is the observed target allocation. And in fact, this was explored by Melfi and Page, and they showed that this allocation does converge to the target almost surely, but it also induces a lot of variability. And extra variability in the variance of the allocation proportions can negatively impact the optimal properties. So Woodruff noted that back in the early 90s, and I guess his student Isley wrote a couple of papers on this idea that you need to do something to get the variability down on this. So in order to reduce the variability, you can get a more general family of functions, which Isley and Woodruff called the doubly adaptive bias coin designs, that kind of take a metric between the observed allocation proportion and the estimated target. So one such metric that I think is a really nice one that Hu and Zhang came up with in the 2004 paper is this one here, which is very similar to Smith's generalized bias coin design that he wrote up in a I guess it was a JRSSB paper a long time ago, or maybe it was a Biometrica paper. But basically, what the y's and the x's are the estimated targets and the observed allocation, and you want a metric that shrinks these things in order to get the allocation function. And this does shrink the variability quite a bit. There's this parameter gamma. If gamma is 0, well, I think that's on the next slide. I'll show you on the next slide. When gamma is 0, then you just get this Melfi and Page design just at the target allocation, estimated target. And that has the highest variability. And if gamma goes to infinity, you get a deterministic design. So you don't have any variability. So it's got to be somewhere between 0 and infinity. And simulations show that 2 to 5 is about right for the value of gamma. So this reduces to Smith's design, interestingly enough, if you're just targeting 1/2. It reduces to Smith's generalized bias coin design. And Smith's generalized bias coin design generalized a whole bunch of other designs. Gamma equals 0 is just coin tossing. Gamma equals 1 is what we called Way's Earn design. Gamma equals 2 is Atkinson's DA optimal design. And Smith actually in his paper suggested gamma equals 5. Okay, so we now have a target and we have an randomization procedure. And now I want to do inference. So the likelihoods look the same for response adaptive randomization as for non-response adaptive randomization, but in fact they're quite different. If we just do restricted randomization, NA is random, but it's ancillary. But in response adaptive randomization, the distribution of NA depends on theta. And so it's no longer ancillary, and therefore we have a set of sufficient statistics. The ordinary sufficient statistics for the binary response case would be the number of successes on A, number of successes on B. And now we have a set of jointly sufficient statistics that include NA. So if you're going to look at the distribution of the usual estimators and test statistics, you need to know something about the joint distribution, or at least asymptotically, the joint asymptotic distribution of these things. So in fact, even if you were doing the usual PA hat minus PB hat, so this would be just your usual PA hat minus PB hat. You would want the distribution of this entire thing over SA, SB, and NA. So when you condition on NA and NB, you lose the information on the design. So in the book, we state as a guiding principle that in order for these procedures to be practical, standard inferential tests should be used. We should be able to use standard inferential tests, which means we need to know the distribution of, at least the asymptotic distribution of the test statistics. Now, the MLE is biased as well. In a paper by Code and Ivanova, you can calculate the bias as the derivative of the expected value, the inverse of the allocation. Now, this thing goes to 0 asymptotically. So you can derive a bias correction if you're interested. So what's the asymptotic distribution of the MLE? So this is in the chapter 3 of the book. So we have for exponential families, that makes the case much easier, although you can generalize to non-exponential families, but in most cases we're only interested in exponential families. We need to first show, for the asymptotic distribution, we need to first show that the target is that the design converges to the target, and then we get the result that the MLEs are strongly consistent and are asymptotically normal, and then we get a formula for the Fisher's information. Now, Alessandra would note that we're too quick to be taking expectations here, because here we've taken an expectation over the NA, which is a design parameter as well. So there is such a thing as a conditional information matrix as well as the Fisher's information matrix here. But this, asymptotically, this is the formula for the Fisher's information. So for example, for the doubly adaptive bias coin design, if we're just targeting Neiman allocation, we have the following result. And that can be used to form tests and estimates and look at the property of estimates. Okay, so we can do inference, and now I want to talk about what are how do we choose a good procedure, and what do we mean by good? So we have a response adaptive randomization procedure that targets rho, and as Alessandra noted, most of these designs of this form have an asymptotically normal limit. Maybe you can find designs that converge quicker, I don't know, but for now we're stuck with this asymptotic limit. So the idea is that we might want to find a design that minimizes the variability. So this property holds for all the designs I've discussed, except, well, I haven't discussed efference bias coin design, so don't even need to talk about it. Okay. So this is a paper in that JSPI. That was a really nice issue that Nancy edited from her Toronto conference. Has a lot of good papers in it. And this is a paper that we had in it that we had a lower bound on the variance. So this is kind of like a Rao-Kremer lower, or Kremer-Rao lower bound, I'm not sure which, for the variance. And so we can actually calculate the smallest that this variance V can be, and presumably that would be a better design if it attains the lower bound. So here's one example. If we want to maximize, if we want to use this is our target allocation. Then for that target allocation, the asymptotically best procedure would have this asymptotic variance. So that's just calculated from that formula now. And we give about 10 other examples in the book. So what actually targets, what designs actually attain the lower bound? Well, the doubly adaptive bias coin design does not attain the lower bound. And hence is not asymptotically best under that definition of asymptotically best. Among the EARN models, which target the wrong thing, Ivanova's design, we showed, is asymptotically best. So you kind of have this trade-off that she has a really nice design with low variability, but it's targeting the wrong thing. And then we have these really nice designs that target the right thing and have higher variability. So which is better? Probably would be best to find the design that targets the right thing and has small variability. So there's a recent paper by Hu, Zhang, and He in the Annals where they find an asymptotically best procedure, and they call it the Efficient Randomized Adaptive Design, E-RAID. The E-RAID can target any allocation and attain the minimum variance. So let me show you this design. So they have a tuning parameter alpha, and if NA is bigger than the, this should be NAJ over J, sorry. These are all proportions. If NA over J is bigger than the estimated target, then you randomize with alpha rho hat. And if it's less than, you randomize with 1 minus that. So it looks a lot like, if you know about efference bias coin design, which I didn't talk about, it looks a lot like efference bias coin design where you have three different values. It's a discontinuous allocation function, so none of the usual theory applies, and so much of their paper is taken up with what are the asymptotic properties of this procedure. But they showed that it attains the lower bound, so it is asymptotically best and can target anything you want. And in fact, efference bias coin design is a special case of the E-RAID when your target is 1/2. And when the tuning parameter alpha is equal to P over 2, where P is the bias of the coin. The choice of alpha doesn't affect the asymptotic properties of the design, but they do some simulations and show that they should select a value somewhere between 0.7 and 0.4 and 0.7. Okay, so you've got the design, and it has good properties, and it's targeting the objectives of the trial, and you want to design the study and tell the person what the sample size should be, and this becomes really quite a mess. So, you know, we have all these wonderful sample size formulas and packages that you just plug in your guess of the variance. But all of those packages assume that NA and NB are fixed in advance. And so sample size calculation is generally considered very simple exercise. But even if you do restricted randomization, you don't even have to do response adaptive randomization. NA and NB have a distribution. They don't, we haven't fixed them. And when you do response adaptive randomization, the distribution of NA depends on the unknown parameters. So, I want to make sure that we preserve our alpha and beta. So that's the number one goal of this our guiding principles is that the operating characteristics of the trial should be preserved. So I want to preserve power, and so I want to make sure we have an adequate sample size to do that. So there's a chapter in the book on this, distinguishing 3 types of sample size calculation. Type 1 is the naive method where we just assume that these allocations are fixed in advance. Type 2 is the average sample size computed over the distribution of NA. And this is another case where did you show me that 5 yet? Oh, good. Okay, good. This is another case where where you know, everyone seems to love taking averages. But what does average power mean? I mean, when you report average power, it means half the time your study is going to be underpowered. So, I mean, in these kind of designs, power is random. So it is a random variable. So I don't like the idea of reporting average power, but you see that on practically every talk. You see the slides reporting average power for adaptive designs. And in fact, I wouldn't want to design a trial where there's a 50% chance of being underpowered. So I think the type 3 makes a lot more sense, where you take a quantile of the distribution over NA. So for instance, we might want the 90th percentile of the distribution of NA, so that we have at least a 90% chance of attaining the requisite power.
I'm sorry, Bill, I've lost it. N is fixed, is that right?
N is fixed, but not NA. NA is a random variable, yes. So in order to compute type 2 and type 3 sample sizes, we need the randomization procedure to converge, and we need it to have a normal limit, and we need to have the known variance, which we do in the ones that I've showed you so far. And this is just some tables that show you what's going on here from, this is just let's just start with simple restricted randomization. So I'm comparing flipping a fair coin to Smith's generalized bias coin design with, I forget what I made gamma here. Oh, I did different gammas. Gamma equals 1, so that's Weiss-Ern design. Gamma equals 5, which is Smith's design, or Smith's recommendation. Okay, so I did different variances. So we have 1 and 2, 1 and 4, 1 and 8, and then equal variances. You see there's not much difference for the equal variances. But if you do the type 1 sample size, out here you get 211. For the type 3 sample size under complete randomization, you get 234. And for the type 3 random sample size, where you have the generalized bias coin design, you get 217. So why is this so much lower than flipping a coin? Because the generalized bias coin, the whole purpose of that design is to shrink the variability. And the variability shrinks as gamma gets larger. So the same principle for doubly adaptive bias coin design, but in this case you're going to see some really dramatic results. So for the doubly adaptive bias coin design, I want convergence to the target. The target I'm using is just Niemann allocation. So I'm only interested in power, not interested in treatment failures or putting more patients on the better treatment. This is just the ratio of the standard deviations. And then we can calculate the asymptotic variance. So now take a look at this table. So we have complete randomization, and then we have the doubly adaptive bias coin designs with various values of our tuning parameter gamma. So if you look at the type 3 design for complete randomization, it's 853. Type 1 design, so just usual standard sample size calculation, 804. And now look at what happens when you use the doubly adaptive bias coin design to target Niemann allocation. You're down to 500. So you're basically in this unusual setting of 1 versus 8. That's kind of unrealistic. But even over here for 1 and 4, you have substantial reductions. 1 and 2, you have reductions. So you can use response adaptive randomization to lower your required sample size, even in the case where you don't do any kind of adapting for being on the better treatment. All you're doing is targeting power with a design that shrinks the variability. So then you could say, well, why doesn't everyone use this? Well, I don't care about that. All right, so let me see. I had a few more comments here. So that's a little overview of response adaptive randomization. I haven't dealt with a lot of issues. I would say that there's been a couple of publications that have come out recently. Someone mentioned the Korn and Friedland paper earlier that appeared in Journal of the National Cancer Institute. Yeah, oh, yes, thanks. Okay, so there's a paper where they take one response adaptive randomization procedure, they do a little simulation table for it, and then they title a paper, Outcome Adaptive Randomization is Not Useful in Clinical Trials. Okay, they don't reference a single paper in the last 10 years, maybe one, they reference one paper in the last 10 years.
Is that code for saying they don't refer to you?
Well, they don't refer to a lot of people, let's put it that way. But, I'm just amazed by, you simulate one design and then you make a general statement like that. It's just, And then, you know, some of you saw the draft guidance of the FDA, and they included response adaptive randomization under the heading, what was it, Vlad? What did it say? Designs, designs that are not well understood. Okay, well.
But they later recognized that that meant to be continued with by FDA.
Yeah, okay, so they're not well understood by the FDA. Okay. Maybe there are a few people that do have a little understanding of them, though. Okay, so I didn't deal with small samples, but of course you want to simulate these designs to see how they work in small and moderate samples. I did not deal with delayed response, which is, of course, something that we deal with in clinical trials. There are results in the book about that. And in fact, when my students, my doctoral students, early on I made them go over to the computer science department and learn how to do a priority queue so they could actually simulate the accrual rate and the delay mechanisms and all of that kind of stuff to see how these do. There are some theoretical results that the asymptotic properties still hold unless the delay is too long, which is defined in those papers. I didn't talk about, I was talking about adapting in terms of patients, but you can adapt in terms of cohorts of patients. That's not a problem. Okay, so my conclusion here is that randomization is usually taken as a standard exercise. Few statisticians even give a thought to its implications. And I gave 5 guiding principles that can be used to find an appropriate procedure, conduct inference, and sample size computations. And then there's 3 properties that we should always consider in designing clinical trials with response adaptive randomization. They should be fully randomized to protect from biases. They should allow standard inferential tests to be used. And they should not impact the operating characteristics of the trial in terms of size, power, and ethical considerations. So a lot of these designs involve tuning parameters that affect the degree of randomization. You remember the gamma in the DBCD, and then there was an alpha in the E-RAID. And you can create an optimal design problem by looking at optimal values of gamma, for instance, for different criteria, such as you could have a compound criteria involving selection, probability of selection bias, and some other criterion like variability of the procedure. So that's something I have a student working on now. And this covariate adaptive randomization, or what some people have called it minimization, some people have called it dynamic allocation. That's a very interesting topic, which is unique. It does not follow the same mathematical formulation. So it has its own theory, and someday maybe I'll give a talk about that, but not here. So thank you.
Thank you very much, and it was excellent timekeeping. I didn't even have to show the 5-minute slide. So there's time for questions.
Alessandra.
You mentioned at one point the play the winner and randomized versions converge to a target which is QB divided by QA plus PB. But it seems to me that a lot of people in this conference are actually have a different target in mind, which is PA divided by PA plus PB. And I never found any theory about that.
I haven't seen that as the solution to an optimal problem, but maybe you know.
But neither is the solution to an optimal problem, but at least with the randomized play the winner, we have
It puts more
an experiment that gets you there.
Yeah, it puts more
but
patients on
with the other one, the PA divided by PA plus PB, what's the experiment?
Yeah,
There isn't.
I don't know. Yeah.
Well,
Yeah,
there is an answer. There is a problem for which play the winner, or a slightly modified, but call it play the winner rule is optimal, which was described by Beckhofer and Kulkarni. And they take a test, well, they take a selection problem, but I think it could be a testing problem, where you have a fixed sample size that you're aiming for on each treatment, and then you try and curtail deterministically when the result is inevitable. And then that turns out to be exactly what you should do to stop with the fewest number of observations. If the two success probabilities are both high, then you minimize the Q over Q plus Q. And if the two success probabilities were both low, you do the opposite. So you can actually have both. But I'm not sure, it's a nice result, but then you think about it and think, well, I wouldn't actually want to solve that problem. I'd change what I was doing. So, but I can give you a reference.
Okay, thanks. Yeah.
The other thing I wanted to comment was just to say, within group sequential testing, you can do a lot of this group by group. And it doesn't seem to, I don't know, that gap doesn't seem to be crossed very often, but Bruce and I wrote about it in our book. And there's one trick we use, which I didn't realize it, so and I can now say then it helps us meet your guiding principle. And it's just that when you're choosing new allocation ratios for the next group, you say, let's change the total sample size for that group, so the information that we're going to get from it is as close as possible the information we're going to have originally under equal sampling. And then your distributions are all exactly what they used to be before you did any adaptation. So you get standard tests, except that they're standard tests for group sequential setting, that they're standard enough. So I think that ought to be cross-fertilized. Because it's you should be doing group sequential things to start with, shouldn't you? So
yeah, I actually, in one paper I had from a long time ago, I said, there hasn't been enough cross-fertilization between design or adaptive design and the sequential analysis. So.
It's chapter 15.
Yeah, I know. It's a beautiful book, by the way. Yeah. That one sells more than 0 copies, I think.
I have a copy of your book. So can you comment a bit on like alpha and this gamma? These are the kind of the more kind of intuitive and try to put a meaning.
Yeah. So, sir, I won't talk about the alpha because the E-rate wasn't my work, and it just came out recently. So, but the gamma is really a parameter that involves how much randomization and how much variability the procedure has. So in simulations, we found that somewhere between 2 and 5 seemed to be okay. But as I say, you could treat this as an optimality problem. You could, if you had some kind of metric for the degree of randomization or the degree of variability you wanted, you could optimize to find the appropriate value of gamma. And that's what one of my doctoral students is working on now. So I don't have any solutions for you yet, but maybe in a year or two, depending on the student.
So it looks like all work was done by your students.
Oh, well, isn't that the goal? Well, that's why we're in academia. Rosemary.
Can I just add a comment? I'm very pleased with your last bullet point. That you're pointing out that covariate adaptive is a completely different ballpark from response adaptive. Because most people just don't realise what a Worm's covariate adaptive is, apart from that talk that we heard a couple of days ago.
But he understood.
Absolutely, but most people have just no idea what a mess that is.
But we've created a monster. We've created a monster with this word adaptive. Period. No one knows what they mean when they talk about adaptive anymore.
And when you add Bayesian.
Well, don't talk about there's a real monster. But sorry, Peter.
It is quiet today.
Okay, with that, I think we have to go to the next speaker. So I have to take the microphone off.